Hello together to the statistics lecture this Monday. Well, you know, I'm still positive. I hope it will end this week. But anyway, although I'm 3 times vaccinated, I was and am still ill. So everybody who thinks nothing to do about Corona, go for it. For Germany, I think if we go on with politics like this over the summer, we will have the next online term in autumn and winter this year. Unfortunately, my forecasts starting from Eastern 2020 were always right that this pandemic will last a bit longer than we think if we don't do anything about it. But anyway, we have learned very much in online lectures, so we can do it anyway. And we will go on with our or finish our revision that we all know what we are talking about here in statistics. And we ended last time with the so-called normal distribution. Was ist das? So, damit kannst du malen. Okay, jetzt musst du mich aber lassen, Aaron. Du kannst was malen, wenn du magst. Okay, so we talked about the normal distribution and especially about the standard normal distribution. And this is quite nice for us because if we figure out that any problem in statistics follows a normal distribution, then we can transform this normal distribution with an expected value of, let's say, 1,000 and a variance of 20,000. Then we can transform this specific normal distribution via this transformation here into the so-called standard normal distribution with expected value of 0 and standard deviation or variance of 1. And this normal distribution, this had this nice feature that it is just symmetric about the 0 axis here, and then everything simplifies in this case. And this, of course, means that we have to translate the general probability that our random variable capital X is smaller than some specific number small x. This means that in a general normal distribution, this would look like this. Then we had here our expected value, and let's say if this value x here is, then this area here would represent p of x smaller than x bar. That this probability can translate it via this general transformation into p of sigma z plus mu is smaller still than x. This is just comes from here. If you take this, you obtain sigma z is x minus mu, and then x equals sigma z plus mu, which we have here. And this then translate, of course, if we transform small x on this side, that we can just take the random variable z, which is standard normally distributed, translates into the same probability of some general random variable capital X. And yeah, this I just gave you the former slide. In general, then we can say, okay, if that is smaller than some specific number C, this is all the left area below the density function now of the standard normal distribution, or if we want to know the probability that our random variable lies in between some specific interval I, A, and B, then it is of course just the area in this interval A and B below our density function. I think this you already have seen in your introductory courses. And then quite often, and if we are going then to significance, to hypothesis testing and so on, then we quite often talk about our hypothesis is true on a level of 99%, on a level of 5%, 95%, or it is fails with a probability of 10% and so on. And therefore, it is quite good if you know these specific numbers here, because these numbers are just the intervals of the standard normal distribution where the area in between these intervals, so from minus 2.58 to plus 2.58, then the area below our density function is 99%. And maybe in some other papers or somewhere else, you all already have heard about my result is true on a significance level of 99%. And this nothing else means if in behind you have the normal distribution, that in the standard distribution, your random variable lies in between the interval from minus 2.58 to plus 2.58. And therefore, it is quite good if you just, when you are doing statistics, if you know these numbers, and especially maybe this is the mostly taken number, is that more or less within the interval minus 2 to plus 2, then you have a significance level of 95%. So maybe this is quite good if you especially know, also not in this lecture, but also in your further life, this number, that 95% in the standard normal distributions is equal, that your random variable lies in between minus 2 to plus 2. Okay, but in order to be more practicable, we will do, just to recapitulate these normal distributions in doing just one little specific questions, and this I hope we can do together. So again, you are chief in charge of quality in a lamp manufacturing company, and the life expectancy of your LED lamp should be normally distributed around 25,000 hours with a standard deviation of 2,000. So, and then at first, I want you to calculate the probability that the LED lamp works less than 20,000 hours. So of course, then if you have any software, you put in your numbers, pushing enter, and then you get your result. But what I want in this lecture, that you know what you are doing. And what does it mean? So we start graphically. Graphically, normal distribution with expected value 25,000 and a standard deviation of 2,000 means graphically we have here our 25,000 normally distributed. And now less than 20,000 just means maybe 20,000 is around here, would mean that you have to calculate the area below these density function. Or if we transform it to the standard normal distribution, standard normal distribution. Now we have an expected value of 0, 25,000, yeah. Now we have to translate. We know that our 25,000 just is now represented by the expected value of 0, but we have to know now the transformed value of 20,000. And here I want you to help me. So, what is then this number? Of course, we know that it has to be on the left side of the 0 axis. If we take our standard transformation from the former slide, if you can give me the number which I have to put here. It is minus, and which number? You know, that is x minus mu over sigma. If we look at here, where do we have it? Here. If x is 20,000, then our specific set is then well, we just put in our numbers. Then 20,000 minus 25,000 over 2,000 is minus 2.5. Exactly. So then we have here our minus 2.5. So now, where my question is, I think all this you should have seen already in your introductory course. Am I not right? Okay, then it was a good point that I have done it again. So we are interested then in this area because this area is the same as this area. Well, and now one possibility to do this is, of course, and I hope you already have seen, tabulas like this, that, remember, our normal distribution is this funny thing with 1 over 2 pi 1 over 2 pi a minus x bar, and for this probability we have to integrate this, and unfortunately this integral has no analytic solution. But since this standard normal distribution is so important, we created, or we just calculated once and forever all specific numbers on a digit level of 2 digits. So this tabular here represents our, I think I can also, oops, this works, no, doesn't want, no, okay, this, okay. These numbers just represent our normal standard distribution. Since we know that our standard normal distribution is symmetric, here of course we have only represent the positive side, positive numbers. So within this table we just have to look up 2.5, because then we know 1 minus this number is the value for minus 2.5. So what do we have to do? Minus 2.5. We go down here, down here, down here, down here, and here we have 2.5. And we don't have 2.53, but we have 2.500. So the second digit is the 0 here, and we end up with 0.99379. This is a probability that our random variable is lower than plus 2.5. But we want to know, so this equals to 0.99379. So roughly 99.4%. What is then the probability that that is lower than minus 2.5? We are symmetric. What we have now calculated is standard of x 2.5. What we now have calculated is this area. But we want to know, I switch here, top, really be a digital guy. We want to know this. Yes, and 0.6, and you have to be specific, but anyway, it is percent, of course. Huh? The whole area below our density function is 100%. If the area, oops, until 2.5 is 99.4%, then this, of course, has to be 0.6%. So this I have done for, yeah, let's say 10 years when I gave my first statistics lecture. And I have to admit, to look up these probabilities by hand in a sheet of paper, this is especially not the thing we should do it. And I don't think that this is real the competence which you should learn in the university. But anyway, this is how most people do it still together. It is like calculating logs with a logarithmic table. Well, of course, we take the log of 25, we put it in our calculator or in some program, pressing enter, and then the number comes out. And therefore, again, I also want to do it with you by Excel, because within Excel, then you still not only pressing enter, but I think that you still know what you are doing. So then let's at first create a standard normal distributed value. So then we take set. Let's say we start from -3 because we want to see in a minute minus 2.5. Take a step value of, let's say, 0.1 plus 0.1, fix it with S4, the double dollars, and then we go down here. And now we need f standard of z. And this is, of course, now this table which we have seen is implemented, of course, in Excel. And this is implemented via normal. I also gave you this list with the translation in English in the formulas, but of course my computer is also in German, the standard language, and therefore we have here the Germans. Then it is back norm word. Then we need here, you see, the x is -3. Now middlewert is mean, standard normal distribution is 0, sorry, and Standardabweichung, standard deviation is 1. And now if we take here cumulated, then it would be the cumulated distribution function, but we want to have the density function, and they are not true but fails. And we need here, I think I can put in here fails or falsch in German, and then we become this number. And now these B4 here, this one, this we can take just down by copying our formula downwards here. And let's go then until +3. Oops. So we have to take this series a bit longer. This file you also get afterwards. Where we are. I think this would be enough. Yes, here we are until the 3. And then we want to have a look. How does it look like? We go down. This is too long. 6. We go until our 3. And to show it, diagrams, and here we are. So this is our standard normal distribution, and now we just want to have this point here by minus 2.5, and therefore we can just look our value up here. Minus 2.5 shouldn't be 0.6. Why isn't it 0.6? So I did anything wrong here. Oh, no. So we need the cumulated value. So it is not this formula here, because this is a number of the density function, but we put it here. And now we want to have the cumulated value. So we change this into true, or in German wahr, enter, and here we have our number and these 0.6 of the probability. So, two other questions. Oops. Calculate the probability that the LED lamp works more than 27,000 hours. How do we do this? In this case, we just want to know the probability. If this is 27,000, we want to have to calculate this area here. Or we have to know this number, which translates from 27,000 into the normal distribution. What do we have to do? Actually, we have to do the same as above here. So we obtain 27,000 minus 25,000 over 2,000 is, yes, calculating that again, and this I just did. Thank you very much. So we need one. Again, by hand, we go in our table, this number, and now it is this number because we want, no, it is not. We want to know the number below. So 84% would represent this area. So this area will be 16%, or this area will be also 16%. Or we go in our Excel file, and this is also a number we already had. We have this number here, but we want again to have the cumulate value. So here it should be 84%, but we need 1 minus this number is our 16%. This is a way how you can do it. Or, of course, if you take a software program, you don't have to go via the standard normal distribution. Of course, you can also just put in not inf, but wert. And now, in the first question, we had 20,000, mean 25,000, standard deviation 2,000, and cumulated. Hopefully, this will also be 0.6. So there's some syntax wrong because I didn't put in here a semicolon. Unfortunately, in the software package, all this has to be right. And here we are. No, this one, and why does this work? I don't know. So percent and 0.6. And we can take, of course, this number, go down here, put it in here. Now 27. And we take 1 minus, and hopefully it will work also. Percent, and here we are. So I really would appreciate if you start to use Excel again. Of course, you have also some other software packages to do statistics, but I really think that if you put your data fully only reading in the numbers and then pressing enter, I don't think that you really know what you are doing. I quite often was sitting in the colloquia of bachelor thesis, and the guys had done anything. They created data and made a statistics analysis, and then I ask, yeah, what is significance? What is the p-value? What are you doing here? What is this probability? And quite often, yeah, the answers were not that what I would have expected. Therefore, I really recommend, yes, you should use software package, but you should also know what you are doing. Okay, I think one is left. Yes, calculate the probability that LED lamps worked within 24,000 hours and 28,500 hours. How do we do the last question? Especially with the standard deviation, when we are doing hypothesis testing and so on, we will do more or less just what we are doing here in our very simple question. Because all of this very complex statistics is more or less translated in the question calculating the probability to some specific distribution, and quite often we assume that the distribution behind our statistics data is the normal distribution. So what are we doing here? Graphically, $25,000. We want to know the area 24,000, 28,500. What we want to know is the area in between here, or translated again. Let's take another color. No. Oh, it's more than 27,000, though it should be somewhere here. Well, of course, we can just, what I showed you in Excel, we just put in the numbers 24 and 28. 500, pressing enter, and we are ready. But also, how do we do it if we translate it into the normal standard distribution? So what we have to know is this number and this number. Quite complicated. Please help me. Now we have to calculate the lower z value and the higher z value. Minus 0.5. This, yes, great. And 1.75. I think you are also right. And what we just had done is 24 minus 25 over 2 is, of course, minus 0.5. And I think you are also right. 28,500 over minus 25 over 2000. This is 3.5 and you have 1.75. Great. Excellent. So, therefore, we could go in our table. What do we have? We have minus 0.5. Let's take another one. Red. Let's take blue. So 0.5 is here. So we are here with, let's say, roughly 69%. And we have 1.75. So we are here. But now we are not going here because the second digit is this one. So just around here. And there we are by around 96%. So what do we have to do with these two numbers? This is the probability for 24, and this is the probability for 28.5. What do we have to do with these two numbers, 69% and 96%? Which area is this? This is plus 0.5, so the 69% is this area, but we want to know the area. Let's take another. Take yellow. What we know is this area here. What is the percentage for the area below minus 0.5? Minus 0.5. If the area below 0.5 is 69%. You know, the standard normal distribution is symmetric. So I really recommend that I will give you also some other exercises to this, if you haven't seen this in your introductory courses. Then of course this area here is also the same area as this area. If the blue area is 69%, what is the yellow area? Standard normal distribution is symmetric. Total area below the density function is 100%. If the left part is 69%, the right part should be 4%. Oh, yeah, you calculated the total. Du musst mich jetzt fertig machen lassen. Super. He's just also learning. He's learning reading. He learns to read. So
bisschen. Das überhaupt nicht.
So, Aaron, jetzt ist gut.
Und
Komm.
das habe ich gelesen.
Komm, du darfst bald auch. Ja. Okay, du darfst bald wieder in die Schule. Sorry. But right now we are 10 days all together here because of this shit corona. Sorry. Your answer 4%. Did you took this here? Because maybe you just then mixed it up. I at first wanted to know the area here. I think then you, if I understand you right, then you just took a step further and you just said, okay, I take 1.75 and then this area would be 4% and we have 0.5 and we need this area. And what we are interested in is this area here. So now we know that this area is 4%, but, and this was the question from here, what is this area? We know that all this area here is 69%. Then we know that this area here is 31. Yes, great. So this area here is 31%. And now we have to know this area we are interested in. That is then 65%. Great. So, and this, yeah, one really has to practice if one is doing statistics. That is not really complicated, but you are not doing this every day, so you really have to practice it. Okay, let's do this also in Excel. So we need 0.5. Then we can just take this formula here. Minus 0.5. Then we are here. Oh, this was the wrong one. I need this one from the standard normal distribution. These are our 31%, and we need 175, and this would be then around here. Up. Didn't work. I didn't copy it, so we copy it, or let's do it here. And then not C29, but we need to have 1.75, and these are our 96, and therefore we obtain 96 minus 39 is 65% as our result. Okay, this took quite longer than I thought, but anyway. So you really haven't seen in your introductory courses calculations with the standard normal distributions like this. This is really true. Well, then it is not your fault, but I don't know what you are doing then in your introductory courses. Only calculating an arithmetic mean or what? Okay. So, because, yeah, then I do not stop here, because now I want to start in a minute with you with what this course should be about, with testing, estimating, hypothesis testing, and so on. But I will also recommend, this is also a very interesting and very important property of the normal distribution. That is the reproductive property of the normal distribution. And this is really, really, really important, this property, because we can say if we have single random variables which are independently normally distributed, that then also the sum of these random variables is also normally distributed. And why is it though important? Of course, x bar, the arithmetic mean, is nothing else than more or less 1x1 plus x2 plus xn. So this is, therefore it is so important, because we can say if our if our random variables are normally independently distributed, then also the arithmetic mean is normally distributed. And what is even more important is that we can also sum up just the variances. And this is then a very simple mathematics we can do if we have these normal distribution. And what we also need further on is the central limit theorem. And here we just take these here we just take these reproductive property, because we just look how behaves our arithmetic mean, our mean of our sample when we created some data. And then we can say, even if we do not know the distribution behind our sample, if our sample is large enough, and this is a reason we just had in Saarland the polls on Sunday, and there you had also, well, we are forecasting that the result of the polls is 40% SPD and 20% CDU, just at 6 o'clock in the evening when the poll ended. And what we are doing there is we just ask around 1,000 people, what was your choice? Where did you make your cross? And this number, 1,000, is statistically quite large. And then we can say, even if we don't know the distribution behind the guys which we ask, where did you make your cross? We can say, okay, more or less the mean of the answers is normally distributed. So that the probability of the mean of some unknown distribution, if we standardize this also, that we can say that the probabilities here, if n goes up, is normally standard distributed. And this is a really, really important result of statistics. And this we will take also if we go then for estimating and testing. Because what we have done until now is more or less only this. Nichts kommentieren. Das muss weg. So. That, yeah, a really important question is, well, we just calculated some means, variances, and so on. We just ask, are these numbers really good numbers? Are these numbers really good estimators for our data set? And this we will do today, that we just ask for some properties that we can discuss, that we can decide this number is really a good representative of our sample. And then, in a second step, we of course then want to ask, is some hypothesis true or false? What is the probability that the value of my investment, given the framework, the numbers are maybe normally distributed, that my investment will have a higher value of 20 million euros in 1 year or something like this. So some general questions we want to answer from some sample which we took from the parent population. The parent population is, yeah, then more or less all data. If we go back to Sunday poll in Saarland, well, of course, we can ask every guy older than 18 in Saarland, where did you make your cross? This is a parent distribution. Then we get the right answer. But then we have, of course, very high transaction costs. Then, because although Saarland is our smallest district in Germany, there are still some around, I think, 1 million people are living there. So we would have to ask 1 million people. But from statistics, we know that it is enough to ask around 1,000 people. Central limit theorem. And then we also have to answer the question from these 1,000 people. We get a result SPD for the percent CDU 20%. To what level of significance? We talked about this when I introduced the standard normal distribution. My result is robust for, let's say, 95%. And this we will do in the next weeks. So we have this parent distribution, a really huge data set. We cannot analyze the parent distribution. It is not possible. It takes too much time. It is too costly. So we just draw a random sample, let's say 1,000 people. From this random sample, we are calculating some estimators where we ask, is this a good estimator or not? And this criteria we will discuss in a minute. When do we generally say that an estimator is a good estimator? And then we take our statistic test and we come to some result. If I'm doing this, then with probability 95% in the future, it will happen something. This is what we are doing in this course. So our random sample is, just one part of our parent distribution. Then, of course, if we take some mean from this random sample, in general, this mean will, of course, differ from the mean of our parent distribution. And this we are calling the sampling error. This is just the difference between our sample statistic, maybe the mean we calculated from our random sample, and the actual true mean of our parent distribution. And quite often, of course, this actual true value of our parent distribution we do not know. Of course, therefore we are doing statistics. And now it is really important also if you are thinking about doing some statistics in your bachelor thesis or something else. If you want to do statistics, you really have to keep in mind that your sample has to be chosen randomly. And at this point, quite often, our sample is misspecified, because sometimes it is quite costly to draw a randomly chosen sample. But if you do not draw a randomly chosen sample, then you are not allowed to do statistics. Because only in this case you can calculate your probabilities from probability theory. So we start with the simplest one, estimation, and this is just the so-called point estimation. This just means we want to determine some specific value, theta hat, to estimate the true parameter from our parent distribution, theta. And theta can be some mean, some variance, standard deviation, proportions, higher moments. This is skewness and so on. Maybe you have heard already from that. And of course, we have to have some specific formula for our estimators. So which estimators we know, and there we can go back here at this point, I hope, to your introductory courses. Well, of course, the maybe most important estimator, the most important value we are calculating is the arithmetic mean of our sample. Here again, if we have here capital letters, then there is meant the random variable, and if we are writing small letters, lowercase letters, then here we mean that capital letter is some specific value. Keep this also in mind, that you distinguish these two cases. What else? If we want to take, if we are interested in some proportions, our balls, if they are right, if they are red or white, maybe you have done something like this in your introductory courses. So we want to know, we have some a glass with white and red balls, 100, and then we take out 10 balls. What is the probability if we have there 30%, 3 out of the 10 balls are red? Can we then conclude that also, or with what which is the probability that we then can conclude that also 30% of the 100 balls in our glass are also red? This is just then a hypothesis. So quite often we are interested in proportions, and this proportion is then just the number k of successes. Here, remember the binomial distributions over our sample size, m. What else? Of course, our variance. And here we have the first difference, I think, to your introductory courses, because I think you have calculated your variance at this point here, not with 1 over n minus 1, but with 1 over n. And why we are using quite often in statistics not 1 over n, but 1 over n minus 1, this we will also learn in this case, in this lecture, because we can show, and in a minute I will define what I mean by unbiased, that if we divide by n minus 1, that then our estimator from our random sample is so-called an unbiased estimator for the true variance of our parent distribution, and this is what we are interested in. So, what does mean unbiased? And now we want to answer the questions: which properties should have our estimators so that we can say these are good estimators? Because, and this you have to keep in mind if you are doing statistics, doing statistics is always doing decision theory, and you are free in your decisions. This is, like your preferences. You have your individual preferences. And if you decide anything else, you are also free. So what you think what is good, this is due to your own preferences. But in general, of course, we can do mathematics, and then we can derive some properties where we would generally say, okay, this is a good estimator. Well, and the first property, when will we in general say that something is a good estimator? So how to calculate our estimator from our sample distribution will be, of course, if the expected value of our estimator is just the true parameter we are interested in. If our estimator has this property, then I think you also think that this is a good property because, of course, we are interested in this number. And if we are interested in this number and we can calculate this number from our estimator, taking the expected value of our estimator, then I think it is generally clear that this would be some property we are interested in. So this means unbiased, because if we wouldn't have here an equal sign, then of course we have some difference between our expected value of our estimator and the true value, and then we would say that it is somehow biased to our true value. So unbiased estimator. We quite often look for estimators which are unbiased, but unfortunately, in some cases, there we can show that there is no unbiased estimator. Okay, and in this case, if we cannot find an unbiased estimator, or also take your transaction costs, if it is too costly to calculate an unbiased estimator, then we take a step back and say, well, of course, I can ask 1,000 people, or maybe I can ask 2,000 or 3,000 people. It is more costly, but if I ask not 1,000 but 2,000, it is more costly, but maybe my budget is high enough that I can also ask 2,000 people. And now, if I have an estimator which is asymptotically unbiased, which just means if if my sample size becomes larger and larger, if this n goes up, this is the sample size. These are the number of the guys which I ask. If this goes up and in the limit I will reach the true value, then this will also be a good property. Because then I have the possibility to be better and better and better, just rising my sample size. But now I do not have directly the equal sign, but in the limit. The larger my sample size, the nearer I'm reaching the true value which I'm interested in. So, what else? And all these properties, this is this is not a really old theory. About this, the scientists thought so in the beginning of the 20th century. All this statistics was created so around 1900, 1910, 1920, 1950, and so on. And then they also said, well, this is nice to have this property of unbiased estimator, but think just about some distribution of these estimators which look maybe something like this. Then, of course, I would be in an expected value. I would reach my true value, but think of the sampling error. In concrete, my sampling error, if I have really a broad distribution, then the probability that the number which I calculate here, the specific numbers, lies maybe here or here. Though the probability that I'm really in the neighborhood of my interested value is quite low. The expectation value matches, but in concrete, maybe I'm be far away from the number I'm interested in. And therefore, another property called efficiency, that I take all unbiased estimators. Maybe I found 4, 5, 6 possibilities to calculate an unbiased estimator. And then, of course, I think it is also generally clear that if I have 5 estimators, all with the property of unbiasedness, that I look up at these 5 estimators and I just take this estimator, which is the closest to my true value. And closeness in generally I will define in variance, so the square distance from my true value, and then I just take this estimator which has the lowest variance. And so if I have the property unbiasedness, and from the set of all unbiased estimators, I take the estimator with the lowest variance. Then I call this estimator is efficient. And again, it's just good. I cannot say this is the best or anything else, because I always in statistics have to keep in mind, what is my question? And due to my question, I look up what is a good estimator. So what else? Consistency. Consistency is something similar like our asymptotically unbiased estimator. And this means, again, in a sequence of estimators, theta n, I will call this sequence of estimators that this is consistent if the probability that my specific number is in between some given specific interval, and this specific interval is just given by the interval theta plus epsilon and theta minus epsilon. And here we have our value of interest, theta, that if I create a sample size larger and larger and larger, that at one point I'm really can be more or less be sure that my specific number theta n hat lies in between some specific interval. So this that the probability that I'm within in the limit this interval is 100%. And this is mathematically, a slight difference to asymptotically unbiased, because I here have a stochastic limit. So if my parameter converges stochastically to the true value, and then I call it consistent. And this consistency is because here I have, of course, this general distribution, and therefore, it is quite often quite abstract to really get an answer. Is my estimator consistent or not? Because it is often quite hard to really calculate this limit given some complicated probability distribution. And therefore, I take also a step back and go to some standard measures to be near or to be in the neighborhood of my true value. And to be near in the neighborhood of my true value, quite often we calculate it via the quadratic distance. And therefore, we call consistency in mean square quadratic distance if the expected value is approaching my true value with the expected value of the quadratic distance. And in general, and this will be your homework, we can say that this difference between our estimated point to the true point can be split off into the variance of our estimated points and some additional displacement. And I hope maybe you have seen this formula again in your introductory courses, hopefully. Because this is also one really important result in statistics, which always comes if you're doing statistics. And the last one is, maybe a bit philosophically, this is the so-called sufficiency. And sufficiency means I take some sample and maybe a very large random sample. And to analyze this large random sample is costly. And now I can ask the question, if I create some numbers out of my sample. So maybe our arithmetic mean or the proportion of my red balls. And then I can ask these aggregated numbers, did I left out now by calculating these estimators some information from my data set? I shouldn't be surprised if this is the case, But the other way around, I can ask, can I calculate my estimators in such a way that I still have all the information of my dataset about the true parameter. And if I find these estimators, this again is a property which I can call good, because then it is possible, if I have, for example, a large data set and my estimator is mapping these data set sufficiently, then this means with some easy calculation, I didn't lose any information of my data I have created. And so I can really reduce high dimensional data vectors to a smaller size, let's say to a usable size. And more or less, this is what Facebook is doing, what Google is doing, what Amazon is doing with your data. They are crawling data and data and data, and now they really think about good statistics to reduce all these data, but not losing relevant information. And therefore, it is a good thing to look for estimators which are also sufficient. And this will then the end for today. Last week I gave you some exercises. We will talk about these hopefully on Thursday, if I have still a voice. And here I have, I think, 10 more exercises. Actually, this is the 10th with a star. This is quite hard. Maybe you can try and ask also the internet to answer this question. But the other questions 1 to 9 we will talk about on Thursday. Maybe not all. And this would be your homework for the next days. So thank you very much today.